to the debate. Our focus today is navigating the really complex world of global climate projections. Specifically, we're looking at the challenge policymakers face when they try to translate the outputs of these huge, multi-model climate experiments, the ones run by the world's leading research centers, into actionable long-term strategy.
Right. And the core of our discussion, it really revolves around how we interpret the uncertainty that comes out of these models. Should long-term planning rely primarily on the multi-model mean, the MMD, that sort of central estimate, or does policy really have to aggressively prioritize the upper bound of that scientifically assessed uncertainty range, to account for the highest end, maybe catastrophic risks?
Exactly. And I'll be arguing today that the multi-model mean provides the most robust, useful, and frankly accurate basis for near and midterm policy formulation. It allows for efficiency and adaptation planning.
And I'll be taking the opposing view. I'm going to argue that relying solely on that average dangerously underestimates the true potential for catastrophic and, crucially, irreversible risk. Therefore, the uncertainty range, especially those high-end warming scenarios driven by nonlinear climate feedbacks, well, that must be the ultimate driver of strategic policy, prioritizing resilience, maybe even survival, over short-term planning efficiency.
Okay, so the strength of focusing on the multi-model mean, or MMD, it's that it synthesizes the collective knowledge from, dozens of these atmospheric ocean general circulation models, AOGCMs. The rationale is deeply scientific. By averaging these independent simulations, individual model biases, and the internal climate variability, what you might call the noise in the system, they tend to cancel each other out. It's believed they compensate. This results in a projection of the future climate's forced response that's considered superior, more reliable than what any single model can offer on its own. This ensemble approach, it gives us extraordinarily clear and, I think, usable benchmarks for planning. So, for example, when looking at high-emission, non-mitigation scenarios like the SRES A1b or A2, the mean warming projected for the late century, say 2090 to 2099, it sits consistently around plus 2.8 degrees Celsius, maybe plus 3.4 degrees Celsius, above the 1980-1999 baseline. That consistency is key. Furthermore, if you look at the very near-term warming, like 2011 to 2030, there's almost no range across any scenario, which confirms that about half the adaptation needed right now is for warming that's already committed, locked in. So the MD provides a necessary, stable, objective scientific baseline, and really all cost-benefit analysis for policy have to rest on that.
I see it quite differently, really, from a different perspective entirely. While the mean, yes, it gives us a tidy, manageable figure, I believe it fundamentally misrepresents the policy challenge, because it fails to adequately account for uncertainty that arises from these nonlinear, high-impact climate processes, most notably the carbon cycle. If we look at the full uncertainty range, especially under the highest emission trajectory A1FI, the warming projection can reach a staggering plus 6.4 degrees Celsius by the end of the century. Compare that to the mean you mentioned of plus 4.0 degrees. That 2.4 degree difference between the mean and the high end, it's not just some statistical tale. It represents existential, unmitigated risk that policies simply cannot afford to overlook. And this massive high-end uncertainty, it's driven primarily by positive climate carbon cycle feedback. We know this from groups like C4MI, the Coupled Climate Carbon Cycle Model Intercomparison Project. Future warming reduces the Earth system's ability to absorb our human-emitted CO2. Under the A2 scenario, for instance, this feedback alone could add, anywhere between 20 and 220 parts per million of atmospheric CO2 by 2100. That's a huge range. When facing such nonlinear, high-impact risk, policy cannot be built on an average. It really must be built on avoiding the worst possible credible outcome.
Okay, so you rely heavily on the idea that these model biases compensate, and therefore the multi-model mean is the most accurate central tendency. I do acknowledge that the mean is technically the best single estimate we have, but let's interrogate its utility a bit. When scientific assessments synthesize these results, They typically conclude that the likely range for future global mean surface air temperature increase falls within about, say, -40% to +60% of the AOGCM mean warming. Now, this framing does make the mean central. We also have high confidence that the range is constrained at the lower bound. It's considered highly improbable that climate sensitivity is below 2 degrees Celsius. Doesn't this evidence suggest that while, yes, the upper bound is large, the most probable outcomes cluster around the mean? And doesn't that solidify its position as the primary planning tool for efficiency?
I appreciate that focus on the central cluster of outcomes, but that definition of likely, I think it only serves policymakers if their aim is for minimal disruption, not necessarily global safety. Focusing on the mean, ignoring a crucial policy insight. These nonlinear risks, specifically the positive carbon cycle feedbacks, they are structurally greater with larger amounts of warming. They amplify the failure rate of any mitigation efforts we might undertake. Consider this. To manage global risk effectively, let's say to keep the global temperature increase likely less than 2 degrees Celsius above pre-industrial levels, a common target, we actually require stabilizing CO2 equivalent concentrations well below 400 parts per million. However, the A1B and A2 scenarios, the very ones that generate your mean outcomes of 2.8 to 3.4 degrees Celsius, are fundamentally inconsistent with achieving that stability target. So, if the mean outcome of a scenario still requires a policy intervention far, far stricter than the scenario itself implies, isn't the mean simply guiding us toward, well, a managed disaster? It suggests insufficient action based on what's perceived as most likely.
But efficiency matters, particularly when we're directing vast public resources. If we know the most probable range clusters around the mean, that's logically where we should direct the bulk of our adaptation funds. Building seawalls to handle the likely sea level rise, adjusting agricultural practices for the likely shifts in precipitation patterns. We have to make decisions now. If we allocate, say, 90% of our resources based on the remotest 5% chance of a truly catastrophic outcome, we risk paralyzing the economy and, critically, fail to address the guaranteed committed warming we know we face in the next 20 years. EMMD gives us that stable, guaranteed target for immediate adaptation.
But that argument seems to prioritize short-term economic calculus over long-term, possibly existential risk management. The very definition of high-impact, low-probability events is that they aren't properly priced into the mean, yet they could carry, well, almost infinite cost. When planning for climate change, we're not just planning for one generation. We are planning for the entire future of human civilization, potentially. The difference between 3.4 degrees Celsius and 6.4 degrees Celsius is arguably the difference between severe disruption and societal collapse. If that carbon cycle feedback is structurally more severe under larger warming, which the science suggests it is, then using the mean for a high-emission pathway is simply accepting that we will overshoot our safety limits. We must set our policy targets based on the required stabilization level, like that 400 ppm target, not the average projected outcome of an unsustainable emission path.
Okay, let's shift then to a specific mechanism of global climate change, one that often generates, let's say, media panic, but where the models actually provide quite clear, centrally guided data. The Atlantic Ocean Meridional Overturning Circulation, or MOC. This is that crucial system, the conveyor belt, transporting warm surface water north and cold deep water south. Now, the multi-model ensemble shows an average reduction of the MOC strength of about 25% by the year 2100 under high-emission scenarios. The range is quite broad, from virtually no change to over a 50% reduction. But here's the key finding, the one that supports planning based on the mean. None of the AOGCMs analyzed show a complete or abrupt collapse of the MOC by the year 2100 for the scenarios considered, and it's judged very unlikely to undergo a large, abrupt transition during the century. So the MMD suggests a gradual, manageable change in ocean circulation, a change we can potentially adapt to over time. This is precisely the kind of reliable projection the mean provides, helping to calm fears of, immediate systemic failure.
I understand the comfort that might be derived from the finding that abrupt MOSC collapse isn't projected this century. Okay, but that finding is necessary, perhaps, but it's insufficient for truly long-term policy. I come at it from a different angle, focusing on irreversibility. While the MOSC may weaken gradually, that weakening is directly influenced by phenomena predicted very consistently across all models, things like high-latitude warming and increased high-latitude precipitation, both of which reduce surface water density in the North Atlantic, which drives the circulation. But more critically, you're focusing on the MOSC status in 2100, and that ignores the irreversible commitments that policy made now must address. Consider the Greenland ice sheet. Scientists model its complete melting as an irreversible process. It seems to begin when global temperatures sustain a level around, 2.7 degrees Celsius above pre-industrial, and once started, it continues, even if CO2 levels are somehow miraculously re-established to pre-industrial conditions later on. We are talking about committing the planet to approximately 7 meters of sea level rise over the subsequent millennia. Now that threshold, that 2.7 degrees C for this civilization-altering 7-meter commitment, it's alarmingly close to the mean outcomes of your A1B and A2 scenarios. If the MMD places us right at the edge of triggering an irreversible collapse, a process that simply cannot be undone, then policy must be driven by the need to stay well below that 2.7-degree trigger, which means we have to target the lower end of the uncertainty distribution, not gamble on the precarious average.
Okay, but even accepting the Greenland commitment argument, the mean projection still allows for a phased policy response, doesn't it? We know the ice sheet melt is slow, it spans centuries or millennia. Therefore, near-term policy guided by the MMD can prioritize cost-effective mitigation strategies now, while adaptation to that very long-term sea level rise can be planned for future generations. And the highest confidence in the eventual magnitude of that rise still comes from the central estimates, from the mean. Why impose immediate, potentially crippling economic costs based on a future outcome that, while yes, catastrophic, gives us literally centuries to prepare, especially when the mean tells us the immediate risks are far more manageable?
Because the mean warming causes the trigger. We're not arguing about how fast the ice melts after the trigger is pulled. We're arguing about whether policy should accept pulling the trigger at all. If the mean warming projection for your, say, business-as-usual scenario is 2.8 degrees Celsius, and the threshold for irreversible 7-meter sea level rise is around 2.7 degrees, well, relying on the mean in that case means accepting failure. Strategic policy demands we manage the concentration risk to avoid the threshold entirely, and that necessitates focusing on the safer lower end of the uncertainty spectrum, not the average. And this brings us squarely to the issue of extremes, which I believe is perhaps the most compelling argument against relying solely on a globally average mean temperature. The largest human cost, the most severe economic disruption, the majority of mortality, it's tied to extreme events, not the smooth global average. The science is quite clear. It is very likely that heat waves will become more intense, more frequent, and longer lasting in the future. The models show that the frequency of extreme warm seasons is projected to rise dramatically. In some mid-latitude areas, extreme summer temperatures, June, July, August, could become 20 to 100 times more frequent than they are now. And critically, these extreme indices, they scale non-uniformly compared to the relatively consistent increases we see in globally average temperature. So the average temperature might rise by, say, 3 degrees, but the number of dangerous heat wave days might quintuple or increase even more. This non-scaling increase in extremes, which is also linked to drier soils and increased drought risk in northern mid-latitudes, it demonstrates that the mean fundamentally masks the true, disruptive nature of the future climate people will actually experience.
Okay, while the intensity of extremes is of course a paramount concern, the multi-model means still provide the foundational, reliable geographic guidance on where these disruptions are most likely to manifest. We might disagree on the precise intensity of a future heat wave in a region, but the MMD gives us high confidence in the overall pattern of change. We see, for instance, highly consistent projections for substantial decreases in precipitation in regions like the Mediterranean and the Caribbean, and corresponding increases at high latitudes. This geographic certainty, derived from the central tendency of the ensemble, allows for targeted, efficient, and proactive regional adaptation plans. We know where to potentially invest in things like desalination and where to bolster flood defenses.
Its policy fixates only on the most remote upper bound scenario for, say, heat wave intensity, we might actually fail to adapt effectively to the geographic shifts in rainfall that the mean clearly indicates are coming.
But the degree of change is the difference between manageable adaptation and, potentially, a migration crisis. The utility of knowing where it will be dry is significantly diminished if the dryness is, say, 100 times more severe than anticipated by the mean prediction. The model results regarding extremes really highlight the failure of the central tendency to capture the potential for regional shock. For example, some models show a shift toward permanent mid-latitude summer drying, increasing drought risk very significantly, while others show less severe drying. If the mean suggests only moderate drying, but the upper bound suggests potential agricultural collapse across a major breadbasket region, policy must hedge against that collapse. The average in this case gives us a false sense of security regarding our ability to manage the intensity of these regional extremes.
But you're effectively asking policymakers to choose the most expensive adaptation and mitigation path based on what might still be a low probability outcome. The MMD is inherently a robust forecast tool precisely because it integrates the largest number of verifiable datasets. It provides structural consistency in the large-scale force response, how atmospheric patterns fundamentally change. This consistency allows for global coordination on the most likely scenario. If we cannot even agree on the most likely path forward, how can we coordinate any effective global action at all? The mean provides the anchor for that global effort.
The anchor should be set by the level of danger, not by the statistical comfort level provided by the mean. The mean outcome under high-emission scenarios is, as we've discussed, scientifically incompatible with widely accepted global safety objectives, largely due to those nonlinear feedbacks that escalate with warming. The difference in risk between the mean and the upper bound is simply too great to ignore for prudent long-term planning.
So to summarize my position, the multi-model mean remains, without question, the most objective and well-constrained scientific synthesis available for understanding the climate system's central response to forcing. It's essential for establishing realistic and efficient policy goals, especially given the clear consensus on near-term committed warming and the structural consistency it provides for adaptation planning across large-scale patterns of change.
However, as I've argued, the mean is an insufficient metric when addressing these critical nonlinear, irreversible, and high-impact risks, whether that's the escalating positive carbon cycle response or the long-term sea level commitment from ice sheets like Greenland. Strategic policy, I maintain, must be heavily weighted toward the upper bounds of uncertainty to safeguard against the most disruptive outcomes, particularly because regional extremes appear to scale so severely away from the global average.
Ultimately, effective policy formulation demands a sophisticated synthesis. I think we can agree on that. We must carefully consider both the central tendency of these complex climate models, which, yes, guides immediate efficient adaptation, and also the high-end risks implied by the full range of physical and biogeochemical uncertainties, which define the outer limits of required mitigation and global safety.
Indeed. The ongoing challenge really is determining the right balance between prioritizing that efficiency, which is often based on the mean, and ensuring maximum resilience, which requires serious consideration of the upper bound of possibilities. There's certainly more to explore here.